Hi everyone, we're going to present counterfactual object masking-based future key state prediction. I am presenter Youngha Jo, and my teammate is Jeongwon Lee, and we're from Green and Cognitive Science Department. Let's begin. For beginning, I'd like to introduce our key inspirations from cognitive science. Humans can make causal judgments about the physical world in everyday life. Like the Jenga image, we infer Jenga might fall or not based on our mental simulation. Specifically, humans can imagine what would have happened if we had removed the objects and infer the stability or which actions to take to make this block stable. And this equals to the counterfactual simulation. Therefore, humans can also predict distant key future states by where slightly different states lead to significantly different state transitions by simulating states with and without specific objects and comparing state transitions between them. Based on the previous findings, here we would like to mention two related papers and contrast to our project. First, mass trajectory modeling partially masked state reward direction and try to reconstruct the whole sequence. However, as in Jenga, we argue that partially omitted state may transition to different states, so we try to address the difference. And for variation temporal friction affects the temporal dynamics to predict sequences, mimicking the human recognition of key states in time. However, we argue that since this boundary detection is implicitly done for just better sequence reconstruction, then this method lacks in addressing why this boundary is drawn here. To mitigate these issues, we try to discover key states in environments by identifying the significant discrepancies between the predicted transition dynamics of masked and unmasked states. So this is our proposed method. We try to use the discrepancies between unmasked dynamics, which has the ground truth, and masked dynamics, which corresponds to the counterfactual. So I'd explain this step by step. So we first train dynamics model without masking for initial stage. And after the initial training, the object is randomly chosen for a random boundary, and this object is masked from the states, and mass dynamics are RMN rollouts using its predictions. If the subsequences before the boundary have little difference like this, whereas the subsequences after the boundary have big differences, we conjecture that then this would be the indicator that the state in the boundary is the key state. So we added this kind of discrepancy before boundary minus discrepancy after boundary as an auxiliary clause to train the boundary detector. So we try to do the experiment in the Angry Birds game environment called 5Q. And since we try to focus on the ability to predict state transitions, we store successful trajectories of length 100 from each random initial states and train the model with this data. And these data are collected from random shooting ages, and we preprocess the data into 6 by 96 by 64, which is shown as figure 8. And lastly, we train the model for a total 50,000 iterations. So let me introduce our preliminary results of how models generate the future states. This is the baseline result where we use this conventional VTA model. Here we highlighted the state where the model marked as the boundary, which is n equals 1. And the model here marked as a boundary when the red bird is on its way towards the gray stone, or the gray stone towards the gray pig. Also, the generated image is somewhat blurry during the red bird, and so overall, the baseline model fails to catch the key states where the red bird hits the gray stone in this scenario. And this is a generated sequence from CS492. In contrast to the baseline model, this model catches the key state as mentioned earlier. As you can see, the model is generating the sequence while capturing the bird colliding to the stone states. In addition, the generated sequences are less blurry in contrast to the baseline model. Finally, for the future work, we only show the qualitative analysis, the generated images, and we have to conduct the quantitative analysis for a thorough comparison between VTA and CS492. And we only tested this on a single scenario, which is shooting stone to destroy the pig. So we need to test on other scenarios as well. And lastly, we are planning to use CS492 as a transition model, and we are trying to train the model-based agent. Specifically, the action of shooting birds can also be interpreted as an intervision, so we can interpret the causality. So we'll try to extend our method to the action as well. Thank you for listening.